I want to answer those. All right, well, we are gonna jump in. So we're continuing atoms in the periodic table. And if you remember this kind of summary slide, we covered these three things on last Thursday. So now we're gonna talk about the periodic table, how it's organized, what we can learn from that. And we're gonna finish with valence electrons. These things right here, valence electrons, this is key moving forward. So please take really good notes when we're talking about valence electrons, because if you don't know how to count valence electrons and you don't know the purpose of them, chapter 3 is gonna be really hard for you, okay? So periodic table. I always love this slide because I love Tetris. Anybody ever play Tetris? We got my grandmother a Game Boy one year for Christmas, and the only game we got her was Tetris. So she literally had just these astronomical records in Tetris for her Game Boy. I still remember it was yellow, and I would try to beat them every time I came over. But I like this joke. This is how they made the periodic table. They just threw it together in a game of Tetris. Not really, right? So we're going to look at all, it took a lot of time to build the periodic table. A lot of things are conveyed when you understand how it's organized. We're going to look at several different ways that it's organized. And that's going to then set us up to talk about valence electrons. So first off, there's two kind of initial sections we can talk about with the periodic table, and those are highlighted. So we've got a purple section highlighted, we've got a red section highlighted, and the purple section is called a row, or sometimes you'll read it's called a period. Okay, a row or a period. So if I say, for example, row 1, row 2, row 3, you need to know which section of the periodic table I'm talking about. So row 1, guess what? I'm going to zoom in for a second. Row 1 right here is just got 2 elements in it. Those 2 elements are just hydrogen and helium. That is row 1. Okay, row 2 is right beneath that. It's got lithium, beryllium, and then these over here, that is row 2. And as you move down, we increase the number of the row. Okay, so the one highlighted in purple is row what? 1, 2, 3. If I said row 4, the first element on row 4, I would be talking about potassium. Okay, so just keep that in mind. Those are rows or periods. All right, the red section is called a group. You'll also hear the word family. Whoops. Or obviously it's a column as well. All right. A group or a family is kind of the main words I use, but you may also read places where it's called a column. So if we're talking about this stuff, if I say group 1, I am talking about all the elements highlighted in red here, and hydrogen is included in that. Okay, it is in group 1. It's just a little bit different from the other elements in group 1, and we'll get to that later. If I say group 2, now I'm talking about all the elements in that column or that group. Okay, so keep that in mind. We've got rows and groups, vertical sections and horizontal sections. Okay, moving down, certain groups have common family names. All right, certain groups have common family names, and those are highlighted here in the different colors. Okay, so I'm actually going to teach you the names of these and a few different characteristics that go with these names. The other groups do not have common names. Okay, so you do not have to know names for every vertical column on the periodic table, but these 4 are very important to know, and I ask that you learn these. Okay, so main group, or sorry, not main group yet, we're not there yet, but group, well, we'll actually get to that. I forgot we have one more slide. So just so you know, we're going to come back to this. These 4 groups have common names, but one other way that the periodic table can be kind of organized or diced up is in these color-coded blocks. So here you see 3 color-coded sections, the red section, the blue, and the green, and these sections as well have common names. And I'm going to teach you those because if I ever say the main groups or the transition metals, I want you to know which section of the periodic table I'm talking about. So in red, we call these the main groups. Main groups, okay? Notice that the blue section is not included in that. The blue section is something different. Even though you have, 1, 2, 3, 4, 5, 6, 7, 8, you have like 10 groups in this blue section. These are different groups, okay? And the blue section is called transition metals. transition metals. So you got main groups in red, and you could number those. Main group 1, I want to do that in red. Main group 1, for example, main group 2, 3, 4, 5, 6, 7, 8. So there are 8 main groups. And then you have the transition metals. And then in green, anybody know what the green section is called? If you've ever kind of looked at the periodic table before, notice there's this arrow here. All of these green elements are actually part of the periodic table, and they should be inserted right here. But that would make for a very, very long and wide periodic table. So for space purposes and printing on like big posters and something, they just pull these groups down below, and they give them their own names. They are called the lanthanides and the actinides. So this keeps moving. Lanthanides and the actinides, lanthanides and actinides. Now, in our course, we're going to spend the most of our time talking about the red and the blue elements, okay, the main groups and the transition metals. We really won't get to the lanthanides and actinides. You have to take just some upper level courses in chemistry, which I know you all want to do, right, to get to the lanthanides and the actinides. But we're going to mainly talk about the blue and the red elements. Okay, so far, any questions on how things are organized? Okay. Last way, I lied to you. There's one more way that it's organized. I know this is a lot. You didn't realize the periodic table conveyed so much information. If you ever see one that's color-coded like this, and I think if you bought a hard copy of the textbook and you open the front cover, you will see your periodic table looks exactly like this one. Okay, so this is kind of the one directly from the textbook in the beginning. But you see here different color-coded sections, okay? Elements in yellow, elements in purple, and elements in blue. What do these mean? Well, the ones in yellow, I'm not going to write in yellow because you probably couldn't see that. All the elements that are in yellow, these are metals. Okay, so if you went out in nature and you found some sodium, okay, or some potassium, it would be a hunk of metal. We're actually going to watch some quick videos in a minute of how these things react with water. Okay, all the transition metals, obviously by name, indicate that they're metals. So they're solids at room temperature, at normal environmental temperatures. They are solids in nature. Now the purple elements, anybody know what the purple's called? There's only a few of these. Muddy? No. They're called are they the gases? Good guess. They are not gases. They're called metalloids. Okay, metalloids. Yes, thank you, Kevin. Metalloids. So these purple ones they have some properties. So they look like metals. They're usually solids, and they can be very brittle or sometimes shiny. Okay, and notice aluminum's right there next to the metalloids, but it's technically classified as a metal. But boron, silicon, so these ones in purple, they have physical properties that are similar to metals, but their chemical reactivity and the way they behave is a lot like non-metals. Okay, so that's why we call them metalloids, because they're kind of like metals in some ways, and they're kind of not like metals in other ways. And then the blue elements, these are all the non-metals. All right, so everything in blue over here on the left side of the periodic table, or sorry, that's the right side. The right side are the non-metals, and the only exception here is you have hydrogen included in that. Hydrogen is a gas, so it's a non-metal as well. All right, so I think that was the last way. Yeah, this is the last way we kind of organize it. So please be familiar with this, because I'm going to ask you where are the metals found on the periodic table, or where are the non-metals found. I may ask you what's the name for main group 1. I may ask you name 3 transition metals, okay? And you need to know which section of the periodic table to go to find those things in, okay? Questions on all these different ways it can be organized? I know it's quite a few different ways here. Now we're going to get to the common family names. So we're going to go back to these main groups that had names, and I'm going to tell you what their common family or group name is. So we're talking about group 1A. Now I'm going to make a distinction here. If you look really closely, I think it's on here. Yeah, if you look really closely at this periodic table, you see things numbered off with A's and B's. Okay, what's that about? Why do some have A? Why do some groups have B's? If you'll notice, anything with an A is considered a main group. Okay, we talked about that earlier. That was all the ones in red. There was all these red elements, okay? We said they are the main groups. So just the way are my eyes deceiving me, or is that, I'm gonna scroll, did magic just happen? Where did my periodic table go? Can y'all not see it too? Okay, well, perfect. I literally don't know what happened. Okay, there it is. Wow. These are the main groups. So anything with an A indicated with an A is a main group. Anything with a B is just a regular group. It's not a main group, okay? All right, so that's what it means. Group 1A, the common family name is the, ALK, alkali, alkali metals. All right, alkali metals, that is group 1. All right, so what we're talking about here is these are obviously metals. We've got Li is lithium, sodium, potassium, Rb, rubidium, cesium, Fr is francium. Now you don't have to remember all the, I'm not asking you to memorize all these names, but I do, we're gonna talk about these metals a whole lot. And so you should get kind of familiar with the names. What you need to know about group 1 is down here. They are highly reactive. Okay, what does that mean? They tend to combine and they form compounds, okay? Because anytime they bump into another atom, the chances are pretty good that they're gonna react with that, okay? So therefore in nature, out in the natural world, we don't ever find them as pure elements. It's very hard to find them in pure form because they're so reactive, okay? And in nature, there's chemical reactions, decaying, things being formed all the time. So they're always found in compound form, all right? That's main group 1. These are the alkali metals. So I actually wanted to show you quick videos. I'm going to stop sharing my screen really quick, and I'm going to reshare my screen with my computer. And we are going to slide over here. Can y'all see this kind of, can y'all see the YouTube panel? Okay, I'm going to, what if I make it big? Can y'all still see it big now? Okay. Oh wait, this is not the one I wanted to do first. We are going to watch potassium, but I want to do sodium first. So the link that I put on the slide actually told me video can't be found anymore. So I just found another one. This is just the reaction of sodium and water. So we're going to watch. I may fast forward through a couple of parts. I just want you to see. Well, he's about to add it. So let's go back up really quick. Sodium and water. I just want you to see what sodium looks like, not in water. He pulls it out and, okay, there it is.
Softer as you go down the column. The sodium is much easier to
turn that off. So you can see, pause right here. This hunk of sodium, okay, is very shiny. There's a few things you notice about it. And did you notice what he just did? He just cut through it with a knife. I'm going to back that up again. He's literally taking a knife, you can see it. So do you think this metal is really hard or really soft? Well, obviously it's soft enough to cut through it with a knife, okay? And when he cuts through it with a knife, I noticed that the inner part is even more shiny than the outer part, okay? So it's a very lustrous metal. And then we're gonna see how it reacts with water. He does some fun stuff with a battery. Is this the part he's putting it directly in water? Okay, so it's here, he has dropped the sodium in water. And can y'all notice what's happening? He kind of zooms in on it. There's that little bead of sodium. It's moving around. Obviously, this is a smaller piece. The larger the piece of sodium, the more, I'm going to use the word violent, the reaction would be. But you can see it's reacting. There used to be a video I would show with a really, really large piece of sodium tossed into like a pond. And it's quite a good reaction, okay? So you can see that there is so much, I don't know what he's trying to do to catch it or what, but it's like, it looks like it's smoking and a bunch of stuff. So that's because it's very, very reactive. Now, again, it's honestly not as, not as expressive as I wanted it to be, but we're gonna watch. Okay, I can't find how to minimize this now. There it is. All right, so that's sodium with water. Ignore the color stuff. Let's go to potassium with water now, okay? So potassium and water, this is a very quick video. It's 18 seconds, so I'm probably gonna play it twice. And I'm gonna turn the noise on, actually, so that you can watch this one.
Yeah.
Or hear it, rather.
Yeah.
Okay, let's back that up. That was pretty quick and pretty crazy.
Ready? Yeah.
Okay. How many of you wish we did something like that in lab this past week? We didn't have anything that crazy. So I'm going to slide back over here and I'm going to reshare back to my iPad really quick so we can talk about these elements. So I want you to think for just a second, what are some of the similarities and what were some of the differences between those two videos with the sodium and the potassium as it reacted with water? So sadly, I don't know why I used to show this video with this link. This link for some reason told me that it couldn't find the video. So if you try to go search that to watch it again, it'll take you to some similar videos and you can just click on a different one. I just Googled or went to YouTube and typed in sodium reacting with water. What were some similarities, or what were some similarities about the way those two metals reacted with water? Can anybody think of one? What happened in both cases?
I'm gonna say like that there is I guess there's like a lot of gas involved, you know.
Yes, it looked like they were smoking, or even with the potassium, it was pretty violent. But I like what Chelsea said, released a gas. There was kind of some fuming or smoking, like I said, coming off. Would you say both of them were pretty visual, right? You could see the reaction. You could see the sodium moving around on the water, and even with potassium, it was much quicker. So they're pretty, like I said, that reinforces this idea that they're what we say highly reactive. Okay. What was the difference between sodium and potassium? Let's look at where they are on the periodic table first. Sodium is right here. And what row is that? Row 3, the first element in row 3. Potassium is also in group 1, but it's in row 4, the row right beneath. So it's the first element in row 4. So they're both part of group 1. They're just on different rows. So what did you notice about the way potassium reacted with water? How was it different than the way sodium reacted?
Like I'm gonna say like it was more violent. Like, yeah.
Definitely. That part was obvious. It was quicker too, right? It took way less time. The sodium kind of hung around on the surface. Again, if it had been a bigger chunk of sodium and more water, then I think you would have seen it could have exploded like potassium. But the potassium was a pretty relatively small piece that he dropped in that bowl of water, and it reacted like instantaneously. Okay. So here's what I know. There's a trend. As you go down group 1, what happens if we were to drop these metals into water and see how they react? Would you say they would become more reactive or less reactive?
More.
Yes, they would become more reactive. So guess probably if we had a little piece of cesium, it probably wouldn't take much at all, maybe the size of a penny or nickel. You could drop that in some water and I mean, the reaction would just be insanely violent. Okay, so as you go down this row, they become more and more reactive. Okay, so keep that in mind. All right, let's go on to group number 2, 2A. The common family name here is very similar to group 1, so don't get them mixed up, but these are the, I always, ALKA, alkaline earth metals. Okay, so we got the alkali metals and then the alkaline earth metals, very similar, but make sure you understand which one's which. Okay, so this is just the one boxed in red here, this is main group 2. You have beryllium, Be, magnesium, okay, and calcium. These are 2 elements you should be very familiar with because you need them in your diet. I remember when I was pregnant with my children, I would take magnesium supplements. Okay, so those are elements you should recognize. Barium down here. So these are the main group 2 elements. And like, very similar to the main group 1 elements, these are also highly reactive. Okay, we typically don't find these in nature very often in pure form. Now they're not as reactive as main group 1, so they're still reactive, but less reactive than main, I'm going to say G1, main group 1, okay? All right, and then we're going to skip over to the right side of the periodic table, all the way to, I'm going to write main group, that should be main group 7A. Okay, so notice it says 7A right here, the A indicating that it is a main group. So the common family name there, anybody know what these elements are called? Anybody heard of these before? Bet some of you have. Surely, there we go. Very close, Emily. Grace got it. Halogens, okay? Halogens, all right? So you have fluorine, chlorine, bromine, iodine are the main halogens that we talk about. These are colorful, okay? They're corrosive. Think about it. When you put a hydrogen with these things, you have a bunch of acids. HF is hydrofluoric acid. HCl, we actually worked with in lab today, hydrochloric acid. HBr is hydrobromic acid. Okay, so these are corrosive. Acids are corrosive, all right? So by nature, these elements, they eat away at other things. They're non-metals, by the way. So like chlorine at room temperature and naturally is a gas. It's a very toxic gas, chlorine gases. Another thing to know about the halogens is they commonly react with group 1 metals to form salts. And in fact, could somebody look at group 1, look at the metals there, and then look at the halogens? Could you tell me a common salt?
NaCl.
Yeah, salt itself, right? NaCl, okay? But we also call any combination of the group 1 and the group 7 salts. So for example, if I had LiCl, lithium chloride, we would call that salt or a salt. If I had potassium fluoride, and we'll talk about how to name this stuff later, we would call that a salt, okay? That's a main group 1 and a main group 7. So any combination of an element from main group 1 with main group 7, we refer to it as a salt, a metal with a non-metal, okay? And if you want to actually watch how salt is made, the reaction between sodium and chlorine, it'll kind of blow your mind, okay? Salt is edible, right? So it's this very docile, edible compound. The reaction is not docile at all. It's very impressive. So I encourage you to go check that out. There's the link if you want to. All right, the last common family name, main group 8. Anybody know what these are called? Kylie said it, noble gases. All right. So what is so noble about these? Anybody remember from your high school science class? Why are these called the noble gases? What do y'all remember about the noble gases? They are stable. Okay. Chelsea said they're stable. That's true. We'll talk about what that means. Anybody else know anything about the noble gases? I just want to kind of see where y'all are at. They don't share. Okay. So they're very selfish. They don't share. They don't share what? Electrons. That's right. They don't share electrons. Okay. Because they have all that they want. Okay, Kevin said the valence shell is almost full. Good. Y'all are set up to do well today. Now, if some of this terminology is brand new for you, that's okay. We're about to walk through what a valence shell is, what a valence electron is. So anyways, yes, the noble gases, because of all these things that everyone's saying in the chat, they are not reactive. Okay, they don't want to be friends with anybody. They have their own clique, and they don't need friends, all right? They're very introverted, you could say. So they're not reactive. You're not going to find them in compound form. That means when you go out into nature, you're going to find them in pure form a lot of time. Helium, okay? Neon, argon, krypton, xenon. So they're not reactive. They are stable, and so on and so forth. Okay. Any questions so far? If I ask you to name the 4 main groups that have common names, you could do that, okay? If I ask you any other sort of, to name a salt between a group 1 and a group 7, you could do that, okay? All right, another thing about the periodic table before we talk about valence is this idea as, this is a phrase I'm going to use, periodicity. What the heck does that mean, periodicity? It just means there's trends. As people have studied the periodic table, they found a lot of different trends, and that's partly why it's organized the way that it is, so that these trends make sense. Okay, these are systematic trends in certain properties. So the first property I'm going to talk about, you're going to have to turn your head sideways, but it's the atomic radius. What do I mean by this word atomic radius? Well, you guys should know what a radius is. If I draw a circle, and here's the center of my circle, remember a radius is just the distance from the outside to the center. It's half the diameter. So we're going to talk about atomic radius. Remember, this is actually a good picture of an atom. The center is the nucleus. I'm going to abbreviate N for nucleus, not neutron, but nucleus. And the outer part's the electron cloud, and we have electrons moving around. By the way, that's one thing I realized I didn't mention last Thursday. You know that table where we talked about the role of protons, neutrons, and electrons? I could scroll back up, but I don't want to right now. Electrons are responsible for the size of atoms. Okay, that's part of their role in an atom. So make sure you put a star down somewhere or go back up to that table where it has the picture of the hydrogen bomb. Electrons, part of their role in the atom is not just the chemistry, but it's also, they make up the size of atoms. Okay, so that's the radius right here, the radius. And when we measured the atomic radius of all these different elements on the periodic table, so these are all the elements listed in increasing number, their atomic number. We saw different trends. We saw certain spikes. Okay, so let's zoom in on these. What do you notice at the peak of those spikes? Which elements seem to have the largest atomic radius? And I want you to tell me what group that is. Because all these elements, Li, yes, group 1, Na, K, rubidium, cesium, francium, these are all main group 1. Okay, so if we go back to a periodic table, guess what? These guys right here, okay, not hydrogen, but these guys right here, main group 1, they have the largest atomic radius. Okay, now what elements, if you look at the bottom of the dips, what elements have the smallest atomic radius? What elements are have atoms that are the smallest? I know hydrogen is kind of an anomaly because it's main group 1 too, but it's very, very small. But if you're looking over here, FClBri, what are those? Those are group what? They're all in the same group. 7A, those are the halogens, okay? So if we go back to this periodic table, these right here are the largest, and these over here, I'm trying to point to 7 there, these are the smallest. So what does that mean? Let's draw a trend really quick. I'm going to come down here and kind of draw the same thing. I'm going to draw a trend in atomic radius. Here's my periodic table. As you go across the periodic table from left to right, what happens to atomic size? Is it increasing or decreasing? Based on what we just talked about. It's decreasing, okay? So I'm going to abbreviate. Atomic radius decreases. I want you to know these trends because there may be times I give you 4 different elements and I say put them in order of their size. And if you know these trends very easily, you can do that. There's one other trend though. What happens as you go down a periodic table? Well, let's just see. As you go down a row, well, let's look. We've got our main group 1, lithium. Would you say sodium has a larger or a smaller atomic radius? The dot for sodium, Na, is definitely, you have to go up. It's larger. And then we got to keep going up to get to potassium. And then we keep going up. So as you go down a group, okay, let's find those elements right here. As you go from lithium to sodium, sodium to potassium, we had to draw up arrows, okay? The size is getting larger. Bailey says, is that because as they get closer to 8, they hold their electrons tighter? Hold on, Bailey. I'm going to come right back to that question. Let me finish this trend. So as you go down, I'm going to turn my screen sideways. Atomic radius increases. Okay, atoms get larger. So the largest elements on the entire periodic table are down here. These are the largest. And then the smallest are right up here. These are the smallest. And hydrogen is included in that. Hydrogen is just such an anomaly in so many ways. It's such an exception. So hydrogen is very, very small. But if we're following these trends, the smallest elements are up here around fluorine and chlorine. Okay, now think about this. Why would the atomic radius, I'm going to go back to Bailey's question. I'm going to pose it to the class. Why would the atomic radius decrease as you go from left to right across the periodic table? Anybody know why atoms get smaller? Bailey said, is it because they get closer to 8? Okay, 8 what? And they hold their electrons tighter. What do y'all think about what she said? Anybody have anything else to say? Why do atoms get smaller as we go across the periodic table from left to right? Anyone? Well, what's changing? Okay, if you go back up to the periodic table, what is changing? Notice, I'm going to just zoom in, for example, what's happening to these numbers right here? 39, 40, 41, 42, 43, 45, 48, 49, 50. As you go across, you're increasing in number. What is that number? You guys are not helping me out.
Protons, atomic number?
Yes, yes, thank you. It's the atomic number. It's the number of protons. So as you go across, these atoms or these elements are ordered in an increasing atomic number. So what that means is the nucleus of these atoms keep getting bigger and bigger by 1 proton and maybe a few neutrons, but we're adding a proton every single time. Okay, element Y has 39 protons. Element ZR has 40 protons. So the nucleus keeps getting bigger. Now imagine what that's going to do if we have a nucleus right here and we've got all these plus charges in there because we know protons are positively charged, and we keep adding a positive charge. The magnitude of that positive charge is bigger and bigger and bigger. And what is that going to do to these negative charges that are surrounding and circling that nucleus? They're attracted to each other, right? It's going to pull those electrons towards itself. And as it does, it shrinks the size of the atom just a little bit, okay? It's not like a crazy astronomical difference, but just a little bit, enough to say that there's a trend, okay? So as we increase in atomic number, we decrease in size, all right? Now, you only can apply that to the horizontal trend here. That does not fit if you try to apply it to the vertical trend we drew. And why is that? Well, as you go down each row or each period, okay, here's what happens. You have a nucleus in the middle of your atom. That's where the protons and the neutrons are. And as you have, so row 1, hydrogen and helium. They're the only elements on row 1. We can draw a circle representing where their electrons would be. I'm going to get more into this in a minute. But as you go down each row, you have to add a layer, almost like layers of an onion. So row 2, guess what? Those elements have 2 layers to their atom. Row 3, those elements have 3. So guess what's happening to the size of the atom? Because we're adding a layer each time, they're getting bigger. That's why the atomic radius increases as you go down. Even though the proton number in the nucleus gets bigger, we're adding an actual layer and we're building the atoms bigger and bigger, okay? So just keep those things in mind. I want you to be able to tell me the atomic radius trends. I want you to be able to order atoms or different elements in order of increasing or decreasing size. Bailey said, so the attraction is stronger, so it's small. Yes, Bailey, that's exactly right. Okay, so that is, I'm really not going to get into melting points. There is a trend with melting points, just so you know, but we're not really going to get into it for time's sake. I really want to get to valence electrons, okay? And I want to save some time at the end. So just know there is also a trend with melting points in this graph. It's really less organized and it's less pretty than the atomic radius trend, but there is a trend there. Okay, let's talk about valence electrons, which we've already mentioned, but what are they? So to talk about valence electrons, we need to talk about the fact that atoms have what we call an electronic structure, okay? We know that different parts of the atom, electrons, protons, they have different charges, positive and negative charges. So I'm going to tell you this, the arrangement of an atom's electrons determines its chemical properties. You could also use the word behavior there. It's chemical properties or it's chemical behavior. How reactive is it? A lot of different other things are indicated when we say chemical properties. Where is its boiling point? Where is its melting point? And a lot of other things. So, but this is all due to the arrangement of their atoms. So what this indicates right here is that atoms are not, or sorry, I keep saying atoms, electrons. Electrons are not free to move around just wherever. Like if you were looking at this center picture, you might think electrons literally just move around like this, okay? That's not the case. Electrons are organized and the arrangement of them is structured in an atom. So this picture over here better represents how electrons can move. They have to move, so for example, this right here could be an electron. They have to move at these certain distances around the atom. Okay, so they have certain tracks or paths they can follow. I don't want you to think they're just going in circles because atoms are actually a sphere and not a two-dimensional circle, okay? But they have certain distances they can and can't be from the nucleus, all right? We call these different circles, like the layers of an onion, we call them energy shells, okay? So these circles right here, we call them energy, that's a Y, shells. Okay, and I want you to think about this kind of like the difference between a ramp and a set of stairs. Okay, what do you know about a ramp? I'm gonna zoom in up here. A ramp is just a continuous slope. You can go up or down it, and you can be at any height. If this ramp had a certain height, okay, you can literally be at any point along this ramp, right? At any height. Okay, so if we're here, that corresponds to a certain height. If we're right here, that corresponds to a certain height. A ramp, you could be at any point, but a set of stairs is not that way. We have a set of stairs, a certain height. You can be here, okay, you can be at this height, you can be here, you can be at this height, or you can be on the top. But you can't be here, all right? You can't be anywhere in between. That's how electrons are. So they can be at certain distances from the nucleus, but they can't just be anywhere. All right, we call these energy shells. So we would say this would be energy shell number 1. And then 2, and then 3, energy shell 4. These are what increase as you go down in row, okay? So an element on row 7 will have 7 energy shells around the nucleus. Does that make sense? All right. Now, the arrangement of electrons, okay, we're talking about electrons here, well, sorry, is determined by the location of an electron and the energy. So we've actually just talked about the location bit. They can have different locations in an atom. Those are on the energy shells. But those energy shells have different energy levels. So they're called an energy shell because they are different in the amount of energy that electrons have depending on what circle or what shell they're on. Okay, so energy shell number 1 is the lowest in energy. Electrons that are found on energy shell number 4. So electrons here have highest energy. Okay, we call them energy shells because electrons on different shells have different amounts of energy. Now I know you're thinking, what in the world does this have to do with nursing and my major in dietetics and speech path? I know this is a very foundational level, okay? But this stuff right here literally explains how all elements behave. And so even though elements may not directly pertain to you and your career, they explain how elements interact with one another and how chemistry happens. So this is important, I promise. This is but just at a very foundational level. Questions so far about how electrons are arranged within an atom? Okay, So now we've talked about electrons, how they're arranged. What is a valence shell electron? Anybody? Anybody want to fill in this blank for me? They are electrons in the outermost energy shell. Electrons in the outermost energy shell. Okay, so if we were looking at this picture up here, any electron on this outer shell that was flying around, we would call that a valence electron. But guess what? Electrons that are on this first shell, they are not valence electrons. Okay. So I wanted to look at the difference between fluorine, chlorine, and bromine to illustrate a point. These are all main group 7. These are all halogens. They're highly reactive. Okay. I'm going to draw a picture of fluorine. Can anybody tell me what row in the periodic table fluorine is found on? What row is fluorine found on? That's what group it's in, Chelsea. It's in group 7A. I want to know what row. That means the horizontal row that it's on.
The second.
The second. Thank you. So we're going to draw a picture of fluorine. I'm going to just come over here. There's the nucleus of fluorine. Okay. Depending on what its atomic number is, tells you how many protons are in the nucleus of fluorine. And because it's on row 2, I'm going to draw 2 energy shells around it. Okay. So the electrons in fluorine that are considered valence electrons are going to be the ones that are on the outermost energy shell. So this second outer layer. Now, I'm going to teach you how to count valence electrons. And in fact, I can't remember if we do that on this next slide down here. Really quick, let's come down here and count valence electrons. Then we're going to go back to our drawing of fluorine. So you count valence electrons. It's very easy. If you know how to count main groups, you know how to count valence electrons. Any element that is in main group 1A has 1 valence electron. Okay, so all the elements in 1A, they have 1, I'm going to abbreviate, valence electron. Remember, we always write electron E with a minus sign. Okay, so guess what? Group 2A, these have 2 valence electrons. So the number of valence electrons matches its main group numbering. So now, how many valence electrons does fluorine have? Well, we've got 3, 4, 5, 6. It is in group 7A. So guess how many valence electrons it has? 7, okay? So let's draw those on here. I want you to draw 7 E's or dots or whatever. I'm going to draw them as electrons. 2, 3, 4, 5, 6, 7. Guess what? There's fluorine, okay? We just drew fluorine. All right, let's draw chlorine. Chlorine's a little bit bigger. I'm going to kind of come over here. Give me some space. What row is chlorine on? Well, it's 1 beneath fluorine. So that means it's on row 3. Thank you. So how many shells, how many circles should we draw around the nucleus? We should draw 3 because it's on row 3. So 1, 2, 3. Now I want you to draw the valence electrons on chlorine. Well, it's also in the same group as fluorine. We go down here. Okay, there's chlorine, Cl. So it should have, guess what? 7 valence electrons as well. So draw those on there. 1, 2, 3, 4, 5, 6, 7. And what do you notice? The number of valence electrons in that outer shell is the same here. And if you go down to bromine, bromine's 1 more down. Quickly, we're going to draw bromine. It's on row 4. So let's 1, 2, 3. I'm going to draw 4 circles. You notice how it gets bigger as you go down in row. And bromine also has 7, but the number of valence electrons, 1, 2, 3, 4, 5, 6, 7, is the same. Okay. And guess what? These are all halogens, and we said all the halogens are pretty reactive. There's a lot of similarities in the way they behave out in nature. And why is this? This is what scientists kept noticing, that when the periodic table is organized this way, there's a lot of similarities in the chemical property of elements in the same group. I'm going to say that again. There's a lot of similar chemical properties for elements in the same group. So what that means, what they found, elements, what we just saw here is that elements that have the same number of valence electrons. There are other electrons in the atom. Okay, we are only talking about the valence. Guess what? There are also going to be electrons on these inner circles, but I'm not talking about those right now. I just want you to focus on the valence. So elements that have the same number of valence electrons tend to have similar group properties and chemical reactivity. So if I pointed out any element on the periodic table, and I said, name an element that's going to behave similar to this element or react similar to this element, what would you do? How could you tell me an element that would behave similar? If I named any element, for example, magnesium, Mg, tell me one element that's going to behave similar to magnesium out in nature. What would you tell me? SR.
Any in the same group.
Exactly. Okay. You just learned a whole lot about the periodic table. And the reason why is because they have similar number of valence electrons. It all has to do with the valence electrons. So all you would do is look in the same group and you would tell me, oh, one of these other elements is going to behave similarly. Now, why? Why does this happen? Okay. Well, like we said, valence electrons are the outermost electrons in an atom. Therefore, they are the most loosely held. The atom holds on to those electrons the loosest because they are the farthest away from the nucleus. They're on the outermost shell, all right? So the nucleus is tugging on all the electrons in an element or in an atom, but it's tugging on those valence electrons the least amount because they're the farthest away. Another thing to note before we pull all the pieces together is that atoms want to have a full outer shell of 8 valence electrons, okay? This is a very, very, very important piece of information. I'm going to put a star by it. There's actually a rule we're going to get to in chapter 3 that describes this exact statement. There is something special, something very stable and very satisfying in nature when elements have 8 valence electrons. Okay, that is considered a full set. Not 9, not 10, not 12, 8. 8 is the magic number, okay? So because of that, atoms have decided in their own society that they will give away or receive valence electrons so as to have 8. Okay, so if we had a constitution for atoms, it would say everybody can do what they want to do to get 8 valence electrons in their pursuit of stability. Okay. So earlier, last Thursday, we said atoms always have the same number of protons and electrons, and they're charge neutral when that happens. But now I'm telling you that's not always the case. In their natural form, if they're by themselves in pure form, yes, they have the same number of electrons and protons. But in nature, things react. And when things react, atoms can choose to give away electrons or receive electrons to get 8. So if we go back up here, I'm going to come back down. So if you didn't finish writing, I'll be right back. Think about fluorine, chlorine, and bromine. What are they going to want to do? How could they get 8? 8 valence. What do they need to do? What do they want to do? They want to, yes, they want to get one more. So they're going to go searching out in nature to find any element that is willing to give up 1 electron. And there are certain elements that are willing to give up just 1, and they prefer to give up just 1. And they really like to react with those. Guess what elements those are? What did we say earlier? We said halogens commonly react with group 1. Yep. Okay. So you're kind of getting a little bit. So for example, another example, an atom with 5 valence electrons. This is going to be any element in main group 5. Can somebody tell me right now one element in main group 5? What element could we be talking about? Someone name any element in main group 5. This could be nitrogen. Thank you. Okay. For example, this could be nitrogen. This is how nitrogen behaves. It has 5 valence electrons. So what it wants to do is it wants to receive 3 more. once it receives 3 more into the valence, and they're literally added to the valence shell, now it will have 8, and we consider that stable. Okay, it's the most stable when it has a full set of 8. Another example, an atom with 2 valence electrons. Okay, here's something different. An atom with 2 valence electrons, it does not want to receive, because notice we said it will give away or receive. An atom with 2 valence electrons would rather give those 2 away, because underneath it likely has a full set of 8. What does that mean? Okay, so let me pick an element with 2. Let's look at calcium. Okay, let's look at calcium. Calcium has 2 valence electrons because it's in main group 2, and that's how you count them, remember? So if we draw a picture of calcium, what row is it on? 1, 2, it's 3, it's the 4th row down, okay? It's the 4th row down. And if we draw a picture of calcium, there's the nucleus. So I'm going to draw 1, 2, 3, 4. Now on its outer shell, it's got those, there are the 2 valence. This is calcium, Ca. So we just said an element that has 2 valence, any element in main group 2, it would rather give these 2 away, because underneath, so if it gives those 2 away, here's what's going to happen. That whole outer shell is going to go away. And underneath, we haven't drawn this yet. It has a full set of 8. So it would rather give 2 away, and underneath it's got a full set of 8 versus gaining 6, okay? So you got to look at what the shortest route is, okay? My goodness. I need to turn all my reminders off. Goodness gracious. Sorry, this is distracting me. Okay, questions on that? I'm going to read this last statement. It happens that elements within the same group have the same number of valence, and therefore they trade electrons. That's why I put this whole figure here. They're going to trade electrons in similar fashion. And all of this dictates the fact that they behave similarly in nature. Okay? Questions on valence? We really are cutting it down to the wire here. We've only got about 15 minutes left, and I want to save some time to work some problems. So I am going to briefly introduce how to draw electron dot structures, and then that's going to be, we're going to wrap up. We might do 1 or 2 of these practice, but we're going to wrap up the content for today so we can focus on some problems. But seriously, if you are confused at all about how to count valence electrons, what this means, the fact that atoms give them away, we're going to get into this really big time in chapter 3. The consequence, or essentially the result of giving away or receiving electrons, how that changes the atom. But this is where we land in chapter 2. I want to show you how to draw what we call an electron dot structure. This is just a really quick visual to show us how many valence any element has. Okay, we're just drawing as dots. Dots represent the number of electrons, valence electrons, not all the electrons, just valence. So I could quickly look at hydrogen instead of going to a periodic table. If I looked at the electron dot structure, I'd know immediately, oh, there's 1 valence because I just see 1 dot. Okay. So as you go across the main groups, 1A, 2A, 3A main groups, you're going to add another dot. Okay, so everything in 1A, you would just draw the symbol, draw the chemical symbol, and you put a dot on any one of the 4 sides to indicate a valence. And then you put 1 dot on each side before you ever pair up 2 dots on one side. So notice carbon's going to have 1 dot, and any element in group 4, 1 dot on each side. Then finally, when I group to group 5, now I'll start pairing them up. Nitrogen has those 2 dots on the right side. And so on and so forth until you get 8. 2 dots on every side. So that indicates. Now, okay, helium, I bet you're wondering about helium. Why does helium not have 8 dots? It's part of group A. It's got 8 valence electrons, right? Well, there is something special about the first row. I'm telling you a quick, again, helium's kind of an anomaly too. A quick exception here. Helium does not have 8 valence, okay? Row 1, so the only elements on row 1 are hydrogen and helium. That's the horizontal part of the periodic table. Row 1, if we draw a picture of that atom, hydrogen or helium here, it can only have 1 shell, 1 energy shell, 1 layer to the onion. And this is more in-depth chemistry that we're going to get into in this class. But that outer row, the very first one, that first energy shell can only hold 2 electrons, and then it's full. Most energy shells are full when they get 8 electrons. That first one is full once it gets 2. It can't hold more than 2. Okay, so that's why when we draw the electron dot structure for helium, we're done when we hit 2. Okay, it's full with 2. It's stable with 2. It's as stable as any other noble gas that has 8. Okay, so that's kind of one exception you need to know about. All right, a really quick practice problem. I want you to give the number of valence electrons and draw the electron dot symbol for atoms of the following elements. Let's just do the first 2, K, R, and C. If you want to practice more, you can do C, D, E, and F for extra practice outside of lecture time. K, R, and C. So go find a periodic table, look in your notes. Tell me how many valence are in that element and draw the electron dot structure. Can anybody tell me how many valence are in Kr?
8.
Okay, we got 8. Okay, so this one has 8 valence. So we draw the symbol Kr, put 1 dot on each side. That's 4. We got to go all the way to 8. So now we can pair them up. That's the electron dot structure for Kr. Okay, C. This is carbon. How many valence in carbon? Bailey said 4. 4 valence. So carbon should just get, I can't do this. I can't put 2 dots on each side. I know that seems technical. Okay, there's the electron dot structure for carbon. Okay. All right, any questions? We've got 10 whole minutes left. I want to work a problem. So I have, I think it's right here. I'm going to jump over to, yeah. I pulled these 2 problems. So these are actually from your textbook, 1.97. If you go to the back of chapter 1, there's just lists of problems. So I just looked through and I found what I thought were 2 good problems. 1.97 and 1.104. I feel like it's really good for us to practice together some more complex conversion problems before the exam, okay? So that's why I'm doing this. Let's work these, and then if anybody has any questions, I'll stick around after. And I have a study session beginning at 9:30. We're just going to work problems if anybody wants to join. All right, this says drug dosages. If you have the textbook, you can literally flip to find this problem and work it with us. You can take a screenshot because I know I don't have it on your lecture notes. So take a screenshot if you want of this. They're typically prescribed in units of milligrams of the drug per kilogram of body weight. Okay, we call that a dosage. A new drug has a recommended dosage of 9 milligram per kilogram body weight. Okay. Part A, how many milligrams would a 130-pound woman have to take to obtain this dosage? This is a conversion problem. We are going to use this relationship right here. So anytime you see a little slash right there relating 2 units, milligram and kilogram, that is a relationship. I want you to use that relationship to convert from pounds, okay, of the woman to milligram of drug. So I want to give you a second to work on that. I want you to try it. Seriously, I want you guys to get out pen and paper. Please, this is going to help you. I want to help you get ready for exam 1. Please do not wait until the end of next week or the middle of next week to start preparing. Some of you right now may be thinking, I don't even know where to start. This is good. It's good for you to maybe recognize that when you go to try to do it yourself, you got to work through how to start the problem. Can anybody tell me where I should start with this?
9 milligrams over 1 kilogram.
9 milligrams over 1 kilogram. Okay, let's do it. So we just wrote out this relationship right here as a conversion factor. Now what are we going to do?
Convert kilograms to pounds.
Convert kilograms to pounds because we have to take into account the size of our woman is 130 pounds. Okay. So anybody know how many, the relationship between kilograms and pounds? Did anybody look that up or have it? It's actually from our measurement slide. I bet if we go down, oh, look right there.
2.2.
Look right there. There we got it. 2.2 pounds in a kilogram. So I want to cancel kilograms. So we've got 2.2 pounds equals 1 kg. I'm going to write this in as a conversion factor. I want kilograms to cancel. So for every 1 kilogram, it's 2.2 pounds. Okay. Now what do? Right now we have milligrams per pound. We just want to know how many milligrams of the drug this woman should take.
Cancel out the pounds by multiplying by how much she weighs.
Perfect. 130 pounds. She weighs 130 pounds. We're going to multiply by her weight. And that will allow us to, we got pounds on bottom, pounds on top now. So now we do the math here, okay? 9. You can plug this into your calculator multiple ways, whatever way it makes sense to you. You can plug it in literally. You can do 9 divided by 1 times 1 divided by 2. Just put these all in parentheses. And then you do times 130 pounds. Or you could literally just do 9 in your calculator divided by 2.2 times 130. You can kind of ignore the ones. But if you don't ignore the ones, I would encourage you to put everything in parentheses. What do we get? How many milligrams does she need to take? Okay, Gabrielle said 531.8. Okay. Oh, that's a lot of pounds. No, it's milligrams. That's how many milligrams of the drug she needs to take. Okay. All right. Let's do part B. How many, we have tablets, 125 milligram tablets should a 40-pound child take to receive the recommended dose? I'm going to give some feedback to this company and say children don't do good with tablets unless they are like ready to dissolve. Okay. Anybody ever try to get a child to like swallow a pill? That doesn't work. Okay. So they should put this medicine in liquid form, but we have 125 milligram tablets. How many should a 40-pound child take? So what are we going to do here? We got a little different style of a question. Now we have tablets. I've got a relationship. 1 tablet is 125 milligrams of drug. Did you notice how the problem didn't necessarily spell that out for you? You kind of had to read between the lines. It's there. The information is there. It says a 125 milligram tablet, but it's important that we could write this relationship out because the question says how many tablets. So we want units of tablets in our answer. Gabrielle, to answer your question, you could round here if that was you were asking about part A. I wouldn't really want you to round to, I mean, you could. I wouldn't count off if you did. All right, so where could we start this problem? Part B. Got a 40-pound child. And again, the recommended dosage is 9 milligrams per kilogram body weight. Why don't we just start with this relationship and say for every 1 tablet, I'm going to abbreviate tab, it's 125 milligrams of drug. That way we know we have tablets on top. Now we just go about canceling any unit we don't want in our answer. So how can we get rid of milligrams? Do we have another relationship that lets us cancel out milligrams?
Nine milligrams per 1 kilogram.
Perfect. This one right up here. This is the relationship. Plug it in so that milligrams cancel. 9 milligrams of the drug for 1 kg body weight. Now we're going to cancel milligrams. Okay, we don't want to know how many tablets per kilogram. We want to just know how many tablets. So we need to cancel kilograms. How are we going to do that?
1 kilogram for every 2.2 pounds.
This one right here, yes. So 1 kg every 2.2 pounds. So this is kind of looking like our problem in part A. We just had an extra step. So now kilograms cancel, and we can multiply by the weight of the child, which is, if you go back and read the problem, 40 pounds. So now you cannot ignore this initial 1 right here. You have 1 divided by 125. You've got to plug in that 1 when you do the math. 1 divided by 125 times 9 divided by 2.2 times 40. What do we get? How many tablets? 1.3 tablets. So about 1.5 tablets. Always round down though, not up, right? So if you had to just give them 1 tablet, maybe that would help. Okay, questions on how we did this? All right, we're kind of at time for the day. I really wanted to get to this problem, but maybe I can do that on my office hour or the study session.